In this video, we're going to discuss how we can use molarity as a tool in stoichiometric calculations. Up until now, we've discussed reactions in solution from more of a qualitative aspect. For example, we've looked at, for instance, taking two solutions, which are aqueous, mixing them together, and looking at perhaps a precipitation reaction that will occur as a result of that. With the addition of molarity into our chemistry tool chest now, we can start to perform quantitative calculations for reactions in aqueous solutions. We've taken a look at this graphic before, in which we take the mass of a reactant, or really anything in our equation, convert that over to the moles, and then use our balanced chemical equation to convert to moles of something else in the reaction, and then finally over to mass. And as we've discussed, moles are really at the heart of that reaction. We have to convert over to moles in order to use our balanced chemical equation to compare two things in our reaction. And what we've been doing so far is using our mass of something in the reaction and the molar mass in order to convert to moles. Molarity now gives us a new way to convert over to moles using the volume of something in solution and a known molarity. And so let's take a look at an example of that. In this reaction, we're reacting together sulfuric acid and calcium carbonate, which will come together to form water, carbon dioxide gas, and some solid calcium sulfate. And so we want to know, in this example, how many grams of our calcium carbonate can be consumed if we begin with 35.5 milliliters of a 0.125 molar sulfuric acid solution. And so, as we've discussed, we can't compare the sulfuric acid and the calcium carbonate on a volume-to-volume or a mass-to-mass basis. We have to compare our moles of sulfuric acid to our moles of calcium carbonate. And so this means that we need to first convert over to our moles of sulfuric acid. And so starting with a volume of sulfuric acid, we can use the molarity in order to do so. And that's what we see in our calculation. We first have to convert our volume to liters, because molarity is in liters. And so once we have our liters of sulfuric acid, we can use our molarity to convert to moles of sulfuric acid. Our balanced chemical equation tells us that it's a 1-to-1 ratio, 1 mole of sulfuric acid to 1 mole of calcium carbonate. And so if we stopped right now, we would know how many moles of calcium carbonate we form, but we want to find the grams. And so as we've done before, we can use our molar mass of calcium carbonate to convert to grams to find that 35.5 milliliters of 0.125 molar sulfuric acid can consume a total of 0.444 grams of calcium carbonate. In this reaction, solid zinc reacts with hydrochloric acid in a gas-forming reaction to form some aqueous zinc chloride and hydrogen gas. And so we want to know what volume of 1.5 molar hydrochloric acid is going to be required in order to convert 24.5 grams of zinc completely over to products. And so here, our starting information is our 24.5 grams of zinc. The first thing we want to do is convert that over to moles of zinc, because that will allow us to then compare it to the HCl. And so we use our molar mass of zinc from the periodic table. And then we can use our balanced chemical equation above to convert over to moles of HCl. We have 2 moles of HCl per every 1 mole of zinc. And now we want to convert over to volume of HCl. And so here we're going to use our molarity of HCl to enable us to do so. we have 1.5 moles of HCl per 1 liter. Finally, the problem does ask us to express our volume in milliliters, and so we will convert over to milliliters. For a final volume of 500 milliliters of the 1.5 molar HCl solution. And so again, this tells us that it's going to take 500 milliliters of 1.5 molar HCl to completely react with 24.5 grams of zinc. Now let's go ahead and put together all of the various tools that we've learned in stoichiometric calculations. In this precipitation reaction, we're going to react together aqueous calcium chloride and aqueous sodium carbonate to form a precipitate of calcium carbonate and aqueous sodium chloride. And so in this reaction, we actually were able to recover 7.2 grams of our calcium carbonate after mixing together 250 milliliters of 0.550 molar calcium chloride and 150 milliliters of 0.750 molar sodium carbonate. So since we have amounts of both of our reactants, we don't know which one of these is going to be the limiting reactant. And so that's our first step. And so first, we'll use our calcium chloride information. So 250 milliliters of our calcium chloride. We want to convert that over to liters, since molarity is in units of liters. Our concentration of calcium chloride was 0.550 molar, so 0.550 moles of calcium chloride per liter. And then we can use our balanced chemical equation to see that for every 1 mole of calcium chloride we start with, we get 1 mole of our calcium carbonate. And so 250 milliliters of 0.550 molar calcium chloride will yield 0.1375 moles of our calcium carbonate. Our next step is to do the exact same thing, but based on our starting amount of 150 milliliters of our sodium carbonate solution. And so, abracadabra, and by magic, we find that 150 milliliters of 0.750 sodium carbonate will yield for us 0.1125 moles of calcium carbonate. And so, since that is less than we receive from starting from calcium chloride, we see that sodium carbonate is going to be our limiting factor, and we will be able to form 0.1125 moles of calcium carbonate. And so we know that we form 0.1125 moles of calcium carbonate, and so we want to know how many grams that is. So we'll use our molar mass of calcium carbonate. And we find that our theoretical yield of calcium carbonate is 11.3 grams. In our particular reaction, though, we were able to actually recover 7.2 grams of calcium carbonate. And so our final step to calculate our percent yield, we will take our actual amount recovered, divided by our theoretical yield, multiply by 100 for a percent yield in this reaction of 63.7%. So in this video, we've looked at using molarity to add one more tool into our stoichiometric tool chest. As we've talked about, in any stoichiometric calculation, the heart of it is our mole-to-mole conversion, using our balanced chemical equation to convert from moles of one thing in the reaction to moles of another thing in the reaction. So far, we've been using our molecular mass in order to convert from grams of something in the reaction, and then back to grams of something else in the reaction. Now, though, using molarity, we just have another avenue in order to get to moles. We can use our volume of solution and our known molarity in order to calculate moles of one thing in the reaction. We could also use our final moles to calculate a volume of something else in the reaction at the end. And so molarity is just one more tool to use in our growing tool chest for stoichiometric calculations. I hope this video has been helpful. If you're looking for more tips on molarity and other types of calculations, be sure to visit the website.